everybody, thanks for coming. This is the second in a row after a long hiatus of Papers We Love. Thanks to PagerDuty for hosting it again. And Leo Zovic is going to present a paper called Pursue Robust Indefinite Scalability. So take it away.
Thank you. So hey everybody, I'm Leo Zovic, or Zovic, also known as Indefinite on GitHub. I'm sort of an incorrigible language nerd, and I like to think about things from different perspectives. And today, I'm here to talk to you about massively distributed cellular automata. So,
Sort of.
Sorry?
Sort of.
Sort of. So the problem that the author of this paper sees is that our current hardware doesn't inherently scale, right? And what I mean by that is if you imagine sort of writing a web application of some kind, some sort of like really basic thing, a to-do app, which I'm sure all of us have written 9 or 10 of, right? One for each language that you know. And you imagine having to run that for 500 users, and you know that this audience is going to generate something like 10,000 hits per month. So that's going to be one system. If you want to run that same program without changing anything for an audience of, let's say, 3 or 4 million users that's going to generate 10,000 hits per second, those are going to be two very different systems, right? If you want to build the first one, if you ask me to build the first one, my response would be, okay, sure, give me a Linode and like an afternoon, and I'll get that coded for you. And the reason that I would say that is the way that you can service that kind of audience is by saying, here is a virtual instance. I'm going to write my application in whatever your favorite language is, Clojure, Python, Ruby. It doesn't actually matter. I'm going to put all of my data in a SQLite 3 database. It's going to live on the same machine as my application server, and then if I'm feeling extra saucy that day, I'll put Nginx in front of it just to make sure that it scales a little bit better than not. If you want to scale this same application to 4 million users and 10,000 hits per second, well, it's not going to look the same way. Right? For starters, you're not going to get away with SQLite 3 in that situation. You're probably going to want to separate your application from your database. You're probably going to want a database cluster that's being interfaced to by an application system. You won't have an application server. You'll have a bunch of application servers. There will be load balancers involved to make sure that none of them go down, or if some of them go down, that you can reroute traffic and all that stuff. There will be multiple levels of caches. So it's not just that we can scale hardware by throwing time and people at it, but it's kind of hard, right? The ideal situation would be if we had a thing that worked at the level of 500 users and 10,000 hits per month. If we wanted the bigger one that worked at 4+ million users and 10,000 hits per second, the ideal situation would be, well, let's just have more of these, right? Let's arrange them so that there's a bunch of them, and then that'll trivially do the correct thing. I don't know whether this system does that. Because as you'll see by the end of the paper, by the way, who's read the paper? I probably should have asked this first. Okay, so a few of us have read the paper. By the end of the paper, it becomes obvious that this is sort of proposing new research into a field of computation that hasn't been as well explored as perhaps it should be. But this is a call for that kind of research to go on. So we don't have answers about whether this actually yields much better or more scalable architectures. But at sort of first glance, based on the stuff that we see coming out of this, it seems like this might provide that level of scalability. In other words, I have no idea how to write a to-do server in the way that you would have to write software in these systems, but it seems marginally plausible that if you were able to write one that serviced 500 users, you could just say, well, now I have a bigger set of tiles to run it on, and now it services 3 million users. That's sort of the basic problem that we're facing down. So let's move on to the hardware that we've got, and that's the illustration that I've got over here is of the hardware. So there's 3 main properties of this hardware. So first off, there's a write-up in here about what the specifications are for a particular tile of hardware that's going to be running these cells. I don't know that that's very interesting because that's sort of a low amount of megahertz and a low amount of kilobytes of memory storage, and it sort of very much focuses on the bits and bytes involved. I don't know that we need to go to that granular level. The point here is that if we want an indefinitely scalable machine, which is what our thesis here is, we need tileable hardware, right? In other words, we need the property that we've got a machine or some number of tiles of these sort of cellular grids that can run computations for us And in flight, we can plug more of them in, and they will just sort of run larger computations. That's all that should have to happen in order for us to expand this machine. That's what tileable hardware means. In order to do that, you basically have to give up the idea of a globally addressable system. Dan, you've got a question. Someone else has a question.
Are we assuming that each tile is like a uniform unit of computation, or is it like a non-uniform set of tiles?
So the proposal in the paper, laid out in the paper, is that each tile is uniform and it has approximately the same behavior,
Okay.
but it has they're all shaped rectangularly. There's no like weird star-shaped tiles or anything like that. And so this is the graph of cells that we're working with is uniformly connected across the entire computation that we're dealing with. And there's some set of specs that are attached to each tile. That's actually one of the points of variance that we can introduce here, right? Because, okay, yes, we could tile things out, but actually, if we're dealing with asynchronous cellular automata, there's no real reason that we can't sort of conceptualize the system as each one of these tiles being their own individual machine, right? You could imagine it that way. It would be weirder and locks would be costlier, and there are locks involved, unfortunately, which I'm about to get into, but you could do it that way too. The sort of interesting synchronization problems happen at tile boundaries. Sorry, where was I before I fielded this question? I feel like that might have been important. That's okay. Right. If we want to be indefinitely scalable and we're working with tileable hardware, what we have to give up in the software layer of this is a global addressability system, global addressing. We can't say, give me information from the cell at global address something, because that address might not exist at the time that we're making that request. And that can happen for both of the reasons, right? It might happen because at the time we make that request, well, that cell hasn't actually been plugged into the giant machine yet, so we might be referencing off into like null land. Or it might be the case that at the time we make that reference, something has exploded and we don't have access to that cell anymore. The way that cells address their surroundings here is via event windows, which is illustrated right here, right? And this is a sort of more of a close-up illustration of that. So the orange cell in the center, when it's that orange cell's turn, has this field of radius 4, knights move in any directions, cells that it can directly address. But it doesn't address them as like, I want the cell at 2732, which I'm not actually sure whether this is that cell or not. If it wants to address this cell, what it says is, I want the cell at 0, -1. In other words, it is the center of its own little universe, and it has an event window that it can see. This is basically visible light cone. It can reference things in a relative fashion around itself, but it can't sort of reach out much further and talk to this other orange cell directly, right? If we want to send messages that survive outside of our light window, we have to do something a little bit weird, which we'll get to in a bit. So we have relative addressing, and we have a small finite window that we can see into and make writes or reads out of. We also can't assume a completely consistent universe, right? Because if we have to do how many of you are familiar with the game of life? Okay, awesome. So we've got cellular automata fans here. If you want to do the lifestyle thing of, of updating the entire world in a consistent fashion, then that implies that every time that any cell runs, you need to lock the entire universe to make sure that nothing weird happens between frames. And we can't do that. The second that we have the requirement of we have to lock the entire universe, we don't have an indefinite machine anymore, right? Or we suffer such horrendous performance penalties that, I mean, I'm not sure whether it's worth it anymore. I don't know whether it's worth it to begin with, but it's definitely not worth it at that point. So when you run, when this orange cell activates, by the way, I'm being very conscious of trying to like point at the correct place, both for you guys and for the video, and that's kind of hard. When this thing wakes up, what it can see is this surrounding area of cells, and it has no assumptions about what kind of state is present outside of that. In fact, the reason that those other orange cells are arranged this way is with this particular size of event window, each of those orange cells might be acting on their local environments independently. In other words, while this thing is unfolding its local environment in a particular way, according to the code embodied in the logic that it's going to run, those other orange cells might be doing the exact same thing right now. And they don't necessarily all have the same rules, right? The asynchronous cellular automaton that we're describing here is like incredibly simple. All it does is pick an event window, lock the surrounding, lock those cells, take the center one and say, okay, you, center cell, if there's anything there, if there's a cell living inside of this, if there's a unit living inside of this cell, run that unit's code and give it as input access to the neighborhood in a completely mutating way. In other words, as part of its logic, this orange cell might be mutating any of the green cells and itself. And so might any of the other orange cells. So like if the orange cells makes a thing here at the very border of its territory that says move to the right outside of its territory, on that cell's turn it'll move to the right. When it's outside of this light window, those other orange cells might make arbitrary modifications to that. So you can't make the assumptions of things I put out into the world are going to stay there. And that's sort of, those are the three basic assumptions that you need in order to code properly for this machine that we're dealing with. Or those are the assumptions that this machine that we're dealing with is going to encode. Okay. In order to program this machine, we're building giant distributed cellular automata. And here's what those look like. So there's actually there's one other thing that I should talk about before that. I'm not entirely sure whether there's a better way of doing this, but the proposed way of solving inter-tile communication is by locking across tiles. In other words, say we have this event window and say that red line there is the tile boundary. In other words, those three green cells above, those are part of some other tile. The green cells below are part of the core tile, the one that the orange cell is acting on. The way that this is going to work is those two tiles are going to coordinate with each other. Hi, there's a question.
Finish your thought.
Okay. These two tiles are going to coordinate so that no one else has access to any of those green cells. Then that orange cell is going to act, and then it's going to give up its turn, and then somebody else is going to act. That's costly because, I mean, network locks are kind of annoying, right? You guys everybody in this audience probably works with them. If you've ever tried to implement them, it's really, I would rather not have them. And you kind of have to do that fairly efficiently if you want to follow the locking recommendations that the paper gives. Go on.
So a tile is a group of cells,
Mm-hmm.
and you said we can think of a tile as also being run within a single machine.
You can think of a tile as being inside of a thread, right? That's what the simulators do, from what I understand. Right? They start up multiple tiles. Each tile runs in its own OS level thread, and the cells on the inside of them have direct communication with each other. The cells at tile boundaries sort of have to do, inter-thread message passing, which has all the problems inherent in that. Okay. So the way that we program for these machines is giant parallel cellular automata. In case you're interested, this diagram here shows the state machine of possible state transitions for locking one of these event windows. Crap, I just moved. There we go. This one down here. So this is fairly complicated, even in the state machine diagram sense. But when you go to implement this, something tells me that this is not going to be simple to implement. So the three basic programs that he shows us how to make in this system are self-healing wire, cell membranes, and daemon horde sort, which, spoiler alert, is just about as cool as it sounds. I'm going to explain them, and then we're going to take a look at a few prototypes that I've built up that sort of build on them and illustrate the concepts well enough that I think you'll understand them. I didn't get to daemon horde sort, even though that would have been goddamn awesome. I built something that's comparable, that will explain the same concepts, but that was sort of at least possible for me to put together inside of a couple of days. Okay, self-healing wire. So remember, we've got finite light windows, right? That's this diagram here. If this cell wants to communicate in some way to this cell, we need ways for that to happen. And one way for that to happen is we've got a self-healing wire that we might extend between endpoints to pass messages along. So remember, each of these cells can arbitrarily mutate its event window environment which includes the ability to say things like, hey, on my turn, what I'm going to do is I'm going to take message atoms from my left and move them to my right. And that's totally fine. Like if you move from event window border to event window border, you can sort of make a bucket chain communication network that extends past light cones. It's just light cones are a thing. So the way that this self-healing wire works is, first off, you've got a receiver and transmitter at either end. The transmitter sends packets along. It's the thing that pulls messages out of some common pool and puts them onto the wire. The receiver is the thing that takes incoming messages from the other end of the wire and then puts them back into that pool of messages to be received and processed somehow. In between are cells that do this bucket chain operation that I just mentioned. So like each of those cells waits for a message to arrive at its origin point, it takes that and it shunts it along. When they get to the other end, the receiver at the other end takes those messages and does something. It's not actually all that important what it does. The self-healing part is each of these cells can regenerate itself. And not only can it regenerate itself, it can regenerate the things adjacent to it. Right? So in other words, the receiver and the transmitter need to be able to know how to lay wire between the other end of the transmitter and receiver. The wire needs to know how to regenerate itself. The other receiver and transmitter need to know the same thing. They need to be able to act in the other direction to make sure that interruptions in service here don't just explode the connection until it's time to do that. The wire, we actually had this discussion at the Friday user group. The wire either needs to be able to figure out how to spawn new transmitters and receivers in case the receiver and transmitter are the thing that explode, or they need to be able to do some kind of search for different connection points after their transmitter and receiver disappear so that they can continue doing their job in the absence of a transmitter and receiver that spawned with them. Okay. Cell membranes are difficult. Cell membranes turn out to be even more difficult than the other stuff that we've got here, mainly because they involve interatom bonds, which is, so they don't actually show an implementation of this, but they mention that there's a quote in here somewhere that says this happens on the hardware substrate in a regrettably complex way. So what we're talking about here is, this is an illustration of a cell membrane over here. So you've got little atoms. Let me see if I can zoom this in just so that you guys have a clearer view of this. I kind of can, sure. This will do. So you can see that there are cells here, but you can also see that there are lines between cells. And this particular implementation of this machine includes sort of non-cell ways of creating borders between regions of the grid. So the idea here is that these are impassable to cells that want to traverse these borders, but they're not actually cells themselves. They just sort of block regions without performing anything on their own. And the problem with this is that these can extend longer distances somehow by a metric I'm not entirely familiar with. This is like the complicated and non-local part of the system. I'm not 100% sure we need it under certain conditions. I think they need it here because of an aggregation property that we can talk about later. The way that these end up working is by insulating computations within a physical region so that they can sort of function uninterrupted from outside interference, right? The idea here is that these things are computing something, or maybe this is just data that's being stored that we don't want to escape out into the world. This is a border around that data. So if there's other computation sort of happening in the substrate alongside this, it's not going to significantly interrupt the operation that's happening in here. This is one of the ways that biomimicry happens in this sort of system, which I fully recognize that this is taking a lot of inspiration from biological systems. One way of insulating certain biological units is by just sort of putting a layer between them that says, I'm going to filter things out from here. And that seems to work. The last piece that he talks about is this daemon horde sort thing. And this is not a very good illustration, so I made my own. This is approximately what daemon horde sort looks like. This is a simplified version. I'm going to show you something that looks approximately like this in a moment. So what's happening here is we've got orange data sources on the very right there. They're spawning these blue things, which are datums, which contain messages that are some number between 0 and, I don't know, 10,000. It doesn't really matter. We've got green bits, which are sorters. And what sorters do is they they sometimes spawn new sorters, but also when they see data atoms coming in, they swap their positions based on the contents of their messages. So the idea is that if, for example, this atom were to see these two here, and let's say that this one contains the value 2 and this one contains the value 15, what it's going to do is say, this one is larger than that one. I'm going to swap their positions so that the lower one is higher and the higher one is lower. And I'm going to shunt them over to the left. That way that by the time they finally make it to these green squares on the very left, these are the endpoints of the sort. These are the things that are going to consume this data. And the idea is that we want the bottom one here to only receive data that is low in the range of values that are being generated by the generators, and we want the bit at the top here to only receive values that are high somehow out of the range of values that are being generated by the generators. What ends up happening if you run this thing is it kind of sorts. So in other words, you get a better than random distribution of values coming in on the left side, but they're not perfect. They get something like 80 or 90% reliability. In other words, you'll get higher values coming in the lower boxes. Sometimes, one effect that Ackley's reported is that in the implementation that he's working with, apparently the more cells that you generate, the better this gets. Like the better the accuracy of this sort becomes.
Does this depend on how long this thing is? The accuracy?
So the claim that he made was specifically that the volume of messages going through it. Like the higher the volume, the more accurate the sorting seems to be, and not necessarily based on the length. I imagine that if you had a longer sorting field, you would get the same effect of things get more sorted by the time they get to the other end. It seems reasonable.
I missed something in the description. Do the blue ones help sort each other?
The blue ones do not help sort each other. They're just data. They move around potentially randomly, but their main function is they contain data and they're being moved by the green things in sort of quasi-organized fashion towards the right-hand side.
So in a real demon horde sort would be a lot more green things.
So in a real demon horde sort, well, no, actually, in a real demon horde sort, there would be a lot more blue things. There would be somewhat more green things.
All right.
We would hope that they're evenly distributed vertically
Right.
too.
And they would basically cover the vertical space.
They would basically cover the vertical space. Like I said, the main reason that I made this diagram is just sort of for illustrative purposes, because this does not at all give you the impression of what this thing is doing. This is more concerned with some kind of interpreter that they hack together in this thing that seems to like deal with something approaching genetic pairs or something like that. If you want, there's actually a talk on YouTube by Dave Ackley. Literally just search Demon Horde Sort. I'm pretty sure it's the only video matching this search. He shows a much better illustration there, including actually showing a running demo of how this thing goes. So that's something to do. All right. Those are the 3 prototypes that he outlines here. And the last thing, which I really like, kind of, is first off, he critiques himself. The 2 critiques that he levels against his systems is that, we've thrown the baby out with the bathwater, which is something along the lines of, this is going to be really hard to program in, probably much harder than building equally reliable systems in traditional computers. And the other one is the hardware costs will be too high and the event rate too low to compute cost effectively, which is, yeah, this is nice and it's robust. How good can this possibly perform? And he admits that both of those are valid criticisms of the approach. But this is the way that we should think about this approach is basically as an alternative to the current standard, which is the von Neumann architecture that we're all basically dealing with, right? The idea is this is a method of computation that says, okay, before we get anything else, before we get to performance, before we get to correctness even, we have to scale and we have to be able to deal with distributed systems that don't necessarily communicate at arbitrary distances from each other. And the computers that we sort of work with don't really do that very well. The idea is that this should stimulate some research, right? We should all go home after having read this paper or heard me talk about this paper and go start building our own prototypes of these systems to try out these ideas and see where they fail and where they don't. And on that note, here are some prototypes of the system so that we can see where they fail and where they don't. So I mentioned already, this is a write-up from my blog of the stuff that I'm about to show you. You can go ahead and read that if you like. I mentioned that I'm in a Matthew on GitHub. There are 2 libraries called Lemon Twirl, also both on my GitHub. They're the most recent ones because they've been updated basically in time for this talk. That you can take a look at some of the code that I'm going to be running. Those of you that have Wi-Fi and open computers right now, there is a thing at twirl.inamathy.ca that you can poke at that will, in theory, let you run some of these machines. You get a reduced instruction set, as you'll see in a moment. Hopefully this works. I'm not sure if this is going to work. I'm not sure I'm on Wi-Fi is the real problem. With that in mind, here is a demo of some of the machines that we've got. So we've got lemon, lime, and orange, which are just sort of, I wasn't sure which ones would show up best on a projector, so I made all 3 of them. And they do nothing, right? These are not robust systems because as soon as, let's say, you throw a bomb in there somewhere, a bomb will explode them. They don't move and they don't reproduce, so they're going to go away if anything bad happens that they don't expect. The next simplest, by the way, we can take a look at the source code for this stuff if you like too. Let's see what the appetite for that is after I've demonstrated what some of them do. Maybe you'll have requests about which one specifically you'd like to see. This is a wanderer, and you can imagine what this thing's implementation says. It says, at the beginning of my turn, I'm going to move to a random empty space in my event window. That's it. It's slightly less robust because if I drop a bomb next to it, it sort of has a chance to move out of the light window of that bomb. But eventually, if I'm sort of fast enough with my clicking, I will kill it with a bomb because it's not always going to change. Okay. This is a bunny, and this one's actually not going to work very well. Let's go with deregs instead. This is a dynamic regulator, which is a little bit different. It randomly deletes things, but it also randomly spawns other deregulators and wanderers occasionally as it goes through. So what you're going to see is these are more robust because A, they replace themselves, and B, they make the wanderers that replace robust because those wanderers are sort of perpetually reseeded. Once you've started a system like this, it sort of expands to fill the space. This will take a while, so we're not going to wait for all of it, but I can blow up parts of this, and that shouldn't matter too hard. Once you get to macro level structures is sort of where I think this gets fairly interesting. Here's a ray. A ray goes to the left. So this thing says, on my turn, I'm going to spawn another ray to my left. And this is slightly more robust than all of the things that we've seen so far because it will replace itself. You can think of this is a demonstration of that self-healing property of the self-healing wire, right? What I've just done is dropped a bomb in the middle of this line, and hey, look, it's going to heal itself by moving towards the left. The problem is that it only moves in one direction, so if I'm clever about it, I can say, haha, I will blow up your right side, and now you have no recourse. So I'm going to annihilate you. But we could get smarter than that. Here's a line. And a line is like a ray, except it's finite, so it's going to stop after a little while, but also it goes in both directions. So if I throw a bomb at this thing, let's say in the middle, what it's going to do is heal itself. But it also is going to survive explosions at either end of itself, right? Each end sort of knows how to respawn the rest of this line. We can get a little bit more complicated by saying, hey, why don't we put 4 lines together into a box? So here's a box. Right? We start at one corner, and what it's going to do is rebuild itself, and this is going to exhibit the same robustness property as the line. If we blow up a corner, the rest of it is going to sort of fill in the gaps. And it's not too bothered which parts we blow up. It's always going to rebuild itself and start continuing to do stuff. All right. All of these are really simple programs. They basically just rebuild themselves. And if that's all we could do, this wouldn't be particularly interesting. So here's the demo that I saw, and you can actually go see the Active video of this. On YouTube, he's got a YouTube channel that is very interesting. I suggest you go through all of it, actually. This is a router. And I'll wait for it to spawn, and then I'm going to explain what it's doing. So the black parts are router edges. The yellow parts are sort of this protective shell. This mimics the cell membrane that we talked about earlier. These yellow parts are going to prevent things from the outside from easily interfering with the operations of the router. They're one event window wide, which means that in order to get inside, you have to either get really lucky in your turn timing, or you have to do something very clever about a timing channel attack on like the underlying substrate. So it's not easy to get through this. Once it's sort of surrounded itself with this protective barrier, it generates what I like to call router bleach. So this stuff on the inside, the light blue stuff, it annihilates anything that's not a router component, which is why you saw that box and those lines vanish. Dan, you have a question or a comment? Okay. Sorry?
Not yet.
All right. The things at the bottom here, the red shinies, they're generating messages. And the messages they generate look like arbitrary strings with an X and a Y coordinate. The green things are endpoints, and they exist in space. They regenerate themselves as a grid of endpoints, and they have addresses. So this one down here is 0, 0. This one down here is 0, 0, 1, or 1, 0. I forget which. But anyway, each of these is sort of designated by an XY coordinate pair that tells you which endpoint this is. The messages start at the bottom. They randomly move through router bleach, and they get frozen when there is no more router bleach, which is what just happened. So now we have to sort of wait for it to refill itself. This is some kind of like robustness. Like it limits the number of messages that can go through the process at any given time. I'm going to speed this up a little bit just so that we don't have to.
Is that intentional, the limiting?
Yes. I don't know why, but yeah, he seems to think that limiting number of messages is kind of important here. I don't know that we would want to seriously, but hey, I'm going to set this at a much lower delay, and we'll see how that goes. So now we're going a bit faster. So you can see the router bleach sort of responding dynamically. The way that this ends up working is messages move randomly, arbitrarily throughout the system on their own, but also the router endpoints move them. In other words, the router endpoints during their turn wake up and say, okay, of the stuff that I can see, are there any messages that have my address on them? And if there are any messages that have my address on them, I'm going to consume them, and then I'm going to spit them out into standard output. That's what's happening here. Each of these lines designate, hey, here's an endpoint, and we found this message out in the wild and consumed it. If it's not for me, I'm going to shunt it a little bit further in the direction that it needs to go. In other words, if its X coordinate is higher than mine, I'm going to shunt it to the right, and if its Y coordinate is higher than mine, I'm going to shunt it up. And sometimes things fall off the grid because they're addressed to router endpoints that don't really exist. That's totally fine. This is working as intended. Okay. That's the basic structure of this router, and I'm going to take advantage of this little dry spell to demonstrate something. Here's a cluster bomb in the middle of it. So we've just annihilated a whole bunch of router endpoints. And what this router is going to do after I annihilate a whole bunch of it is it's going to rebuild itself, and then it's going to keep routing. And this is the part that really made me interested in this style of computation, because up to the point where I saw this YouTube video, there is no system that I had built that can sort of tolerate the destruction of 3/4 of itself and just sort of, yeah, okay, let's rebuild, and then let's continue from where I was going. So you lose a little bit of data when you do this, right? The bombs might take some of the messages that we want to route out with them, but there's no point at which this entire system is going to halt as a result of 3/4 of it being destroyed. And that's what I mean, that's what's meant by robustness, right? We want to be robust in the face of massive failures of large percentages of our infrastructure, and still keep going in the face of that and provide working computation. This is really hard to build, by the way. This was not much harder than I was expecting, but it's possible that I just don't have the right intermediate language to express this sort of cellular automaton in it. But this sort of took a little bit more code than I was expecting, and it took a little bit more friction than I thought it would in a few different ways. One of the interesting ones is actually, okay, let me show you a thing. Here's gray goo. How many of you know about gray goo? So gray goo says, during my turn, spawn self in everything. And if you let that happen, it sort of eats the world. One way to implement a router would have been to say, okay, that router bleach, that's actually gray goo with a whitelist. Right? I can't implement it that way. You can see that it sort of conquers territory ahead of the router and then stops at that designated boundary. The reason I did this was because I had to sort of box it in. If you make that gray goo with a whitelist, which would be a much simpler program, right? It's easier to do that than what I had to do here. What you end up getting is the situation where, one, you really need to check that the router is completely enclosed before you can spawn any of that stuff on the inside, and two, you have to hope like hell that nobody comes along and opens up your router in a way that lets some of the gray goo escape, because then you've just created like something between a mass extinction event and a hazmat spill inside of your software. And that's a little bit weird, right? There are other problems that are involved in programming these computers than we're. There are other problems involved in making programs like this than are involved in making the traditional programs that we're sort of used to writing. But it seems like they exist, and it seems like we need to think a little bit differently about them rather than being a bit easier. Okay. I think I'm going to stop there. I think that's enough sort of giant piles of words and new concepts for you guys. Do we have questions? Do we want to discuss any parts of this? Yeah.
So presumably, like, I'm just thinking, like, by analogy, when a cell breaks open and leaks something out in your body has mechanisms to deal with that problem, right? Yeah. And so, like, there should be an analogy in programs written like this, where if the gray goo gets out, there's something that can...
Well, so there is, right? And this is I'm really sorry that you're making me go here, but the grisly analogy would be somebody getting shot in the stomach, right? Your stomach acid leaks out and eats you. And that's not, you kind of hope that doesn't happen, is what humans do.
All right. Is cancer an analogy too?
So cancer is probably the best analogy I've got to this gray goo thing, right? This is the cell that consumes everything in its path and consumes and like envelops all resources. This is the thing that happens if you have completely unchecked growth across everything. It eats everything else. Yeah, we don't want that to happen either, and that's totally a thing that could happen if the way that these distributed systems work is we have to run code that we don't trust on them. And there are ways of dealing with that. I think so it's not in the paper, but if you talk to if you talk to Ackley, or if you read some of the other material that he's written, or if you take a look at the source code that he's got, apparently one of the tactics that he's got against this is in his real production systems. What happens is there is a cost associated with spawning yourself. So it's not possible for a cell to just say, I want all of it forever. Because what happens if a cell does that is it quickly runs out of resources and then it can't get anything. And that's sort of the situation you want, because then you don't get the situation where a particular cell can run rampage and consume all resources.
Right. Yeah, if we think of these running like in the cloud,
yeah,
then there's kind of a binding of economic resources to the processing. And that helps a lot with problems like gray goo.
The other thing is, oh, sorry.
No.
Go ahead.
Sorry. So why strictly 2 dimensions? So
there is no. That's one of the points of variation that I'm actually kind of interested in. So the question was why strictly 2 dimensions? I don't know how good this thing is, so I felt like I had to repeat your question. I've got a 2D world of cellular automata here, but there's actually no reason that we can't have a more tightly connected graph of nodes, right? We don't even necessarily need a uniform one in order to run computations like this. So number of dimensions is one of the things that we might consider exploring as other stuff. I'm not sure how useful actual 3D chips are. I don't know that we're there yet, but that seems like a thing that might be more useful. We can think about more dimensions because these are virtual grids. But if we think about more than 3 dimensions, it's harder to implement that in hardware, right? And we need to do some other tricky things.
It's probably harder. 2 is probably our current.
I mean, okay.
Yeah.
There are, for example, for synchronous cellular automata like life, there are variants that are 3D. Right? There is 3D life that actually has fairly good unfolding rules and decent interesting properties that you can observe. I don't know why those haven't been more explored. And I don't know that Ackley has answered questions about why he would not explore those. Is that okay?
Just to speculate on that, there's kind of a physicality to these visualizations, right? Like you have to line things with boxes and then put things inside them and kind of arrange them in certain ways for it to all work. And I wonder if that's somehow harder to analyze in 3 dimensions, because once you've wrapped it in a box, it's hard to look inside that box.
Yeah.
Whereas with 2D, we kind of get this 10,000 foot view.
I'm just going to try to do something here because I want to show you something that might answer the question or give you an indication of it. So this is a unit that I didn't show you earlier because it's white, and unfortunately on this projection the background is also white. It's actually a light gray, so you can kind of see the contrast. But here are bunnies. Oh damn it, I actually need to refresh, don't I? Yeah, for the CSS changes to take place. So here are bunnies. I'm going to spawn a bunch more of them on the other side. What a bunny cell does is during its activation, it checks how many other bunnies it can see. And if that number is below a certain threshold, why are you not spawning? Oh, it's because I refreshed. And if that number is below a certain threshold, it's going to respawn itself. And and it also moves randomly like a wanderer does. So this is a different approach to the dereg approach that Ackley proposes. So, okay, let's unpack that a little bit. One of the self-regulating approaches to population that Ackley proposes is the dereg approach, which the idea is that you have resource cells. And you also have dynamic regulators, which is what dereg means. Deregs spawn other deregs, and they also spawn resources, but they also randomly delete resources as they aggregate throughout the system. The way that they do this is not by paying attention to their environment at all. The way that they do this is basically by a dice roll. There is some probability that on each turn that a dereg takes, it will spawn another. It will delete something randomly from its environment. There is a somewhat smaller probability that it spawns a resource cell, and there is a much, much smaller probability that it spawns another dynamic regulator. But this probability is independent of where the thing is. And this is one method of population control. You say, well, what is the probability that given a long enough time scale, I will expect to arrive at the population that I expect for this particular cell? Let's set those in code as this is my population. The other approach to population control, which this is the one that sort of gets harder the more we think about non-blocking models of these automata, and we can talk about that after I've explained the problem, which is this approach here, in which the cell wakes up, takes a population tally of the event window that it can see, and then based on that tally decides what to do. Right? This is sort of modeling more like an anthill than like a dice roll. Based on how many things you see of a particular kind, you're going to decide what to do yourself as your next step. Doing this sort of work gets a little bit trickier in more dimensions, right? It's relatively simple to check a 2-dimensional grid for this kind of, to do a census of a 2-dimensional grid. It might get harder in 3-dimensional grids, and it definitely gets harder in like arbitrarily connected graphs. That might be one reason, although I realize that's sort of a non-reason, right? If we had the appropriate interface, depending on what the underlying implementation was, this would be approximately as easy to work with. It might be more or less efficient to implement.
One of the other properties of or one of the advantages of von Neumann of this is that it becomes very easy to analyze, it's tractable to analyze algorithms. And in like a deterministic way, like I can look at a sorting algorithm and estimate how much memory it's going to take.
Yep.
But with this, it's like completely statistical analysis, which is not
as
easy.
I'm glad you brought this up. So the performance measurement that Ackley proposes is event per site second, which is how many events are happening on the grid at a particular time. I don't know that tells us much about how effective different algorithms are versus different other algorithms. And I know exactly why you're asking, right? I would really like to know what's more efficient, like which kind of approach to population control is more efficient at different scales. Yeah, it seems like at a first glance, it seems like statistical is the right way to do this. And not only that, but it's sort of, you have to build that into the hardware, right? Like, it's not that I could program a bit here that says something like efficiency tracker and then spawn a bunch of them and then it'll do my efficiency tracking for me in my program. I sort of need those tiles that I'm building the system out of to be able to track what's going on at different cells and to figure out, okay, what kind of events are firing, how frequently, and what is their distribution. And then I might need higher level unpackings of those statistics to figure out, okay, given these low level hardware statistics, what does that actually say about my program? This sounds like a really hard problem. Like, this sounds like the sort of problem that we run into when we deal with traffic distribution amongst distributed networks in real life right now, as opposed to the kinds of analyses that we run on source code. And yeah, that gets hard. Dan? Oh, sorry. Do we?
Go ahead.
No, I was just going to suggest maybe it's 2D for hardware reasons, because I remember once IBM tried making these sort of grid box machines where you have little boxes, you stack them like 10 wide, 10 tall, 10 deep or something like that. They said there's a problem with a huge problem they had is heat in the middle, because when you have a lot of these machines stacked in 3D form, the middle generates a lot of heat and kind of dissipated, so they had some complicated system for dissipating heat. So perhaps they're trialing it's a hardware thing.
This is what I meant. What I meant when I mentioned I don't know that chips have gotten to 3D yet. The last I heard was heat dissipation is a problem, and I don't know that we've gotten past that. I don't know how you would, other than periodic heat sinks or something. So yeah, this would be a good. This might also be a reason that 3D is not a thing in this representation.
Has anyone built a movable feast in movable feast too?
No. I feel like someone might have done this in Minecraft already, and I mean, if not, I mean, I'm not going to call dibs, but maybe one of you guys can beat me to it. Let's race.
In fact, do you know of anything genuinely useful built in this?
No.
Right.
Right now, this is sort of, as far as I understand, this is a giant thought experiment to, hey, what if we build software and the corresponding hardware to be this robust out of the gate?
Has any work gone into, well, I'm assuming some work has gone into this,
Mm-hmm.
but like, I know Stephen Wolfram has been talking about cellular automata as like a new way of computing or whatever for a really long time. What about like representing data as cellular automata, like numbered sets?
Mm-hmm.
So
this actually goes to much before Stephen Wolfram. There's a few papers, or I don't even know if it's necessarily papers, but I know there's a few sort of demos that von Neumann was working on back when he was working and alive. The von Neumann architecture that we're using as the underlying substrate for our entire world of computation, that was sort of meant as a 1.0, right? This was a first stab at something that definitely wouldn't scale as far as we've managed to scale it so far. The next level up of the architecture that he was thinking about was, okay, well, how about we describe things in this sort of self-replicating cellular automata style? Those programs can go off and do things that we don't necessarily control centrally, and what would that look like? So this is already stuff that's been, a long time coming. It's an interesting question, because cellular automata are Turing complete, right? There's Brian's brain that has been shown that was the most minimal automata that we can show to be Turing complete. So in fact, if you make wires that represent OR and NOT gates, you get all of programming in this anyway. I don't know that there's been as much work in asynchronous cellular automata. I imagine they're a lot less consistent on some level. But you could probably do that same sort of thing here, right? Just represent programs in this way, and they would sort of not look very organic. They would look alien to us, and they would move in bizarre, sort of oily ways, but they would live and do the computations that we want, and then we would have to sort of hook into them and decode the outputs in order to figure out what it is that they're doing. I'm not sure that there is very much work on this. Right. The only system that I know that works anything approximately like this is one that we're all sort of interested in and aware of, if you conceptualize it as a computer system, and that's the internet, right? This is, if anybody's listened to Kevin Kelly speak, if you think of all computers as a computer because they're networked, that's sort of what we've got here, right? That is the infinitely scalable set of computers that we can keep connecting things into. There's kind of a global addressing scheme, but there's a ton of hacks around it to make sure that we don't actually run out of global addresses, and also there's subnetting so that we can have local networks hiding as single nodes on the global network. That seems to have worked, because the internet hasn't yet turned off, although I know that we're in the year 2017 and maybe that's about to change next week. But so far we've done pretty well with this one, so it seems to be robust. But that's the only example that I can point to and sort of say this style of computation has something to offer that's useful.
We're moving to going to a bigger address space in
Yeah.
the internet, and I think I just looked at the stats. It's about 20% of the internet now, and it looks like it's the flat part of the S curve.
Right. So we've hit the point where we're not scaling anymore. Right.
No, this is IPv6
Oh, I see.
penetration.
I see. Yeah. Yeah. And that's
So
that's a legitimate
basically those
approach.
hacks are going to go away.
Yeah. Okay. Good.
This is also, sorry.
No, go ahead.
This is also quite a bit different than trying to encode data in cellular automata, maybe.
Yeah.
Like we're sort of at a higher level of abstraction than trying to actually make programs in the game of life, for example, which is a very low level of abstraction, and you need to use millions of cells to encode anything reasonable. Here, each of these cells is actually a program. Like there's some code in there, there's some data inside there.
Okay.
If we want to take a look at what that looks like, actually, I do have source code, and like I mentioned, these repos are all on GitHub, so you can do your own exploring.
Too
Sure.
far away from
Yeah.
the one we were just running. I just had a question about, it seems to me like this system should know the size of the system you're running in.
Mm-hmm.
So how, like when we're drawing these box lines,
Yeah.
what is telling the node to stop at node, like, for the router, the gray line, it's telling it to stop at 54 or 55. It'd be like, that's the end of your router, because you started so far away.
Mm-hmm.
Do you know the size of the system you're running in? I thought you only knew like the 5 around you.
Yeah. So you don't know let's take a look at what these things look like. I think this might mildly disappoint you, but not by very much.
You can't address anything that's more than 5 away.
So how do you ever know when to stop for
You
the
can-
size of your block?
When you propagate a new thing, you also tell it how big we're ultimately going to get, and it says, oh, I'm this far away from the start, and it needs to get this big.
But you can only see 5 away from you. You
But
can't know your starts there anymore.
But I can say you're
it
5
keeps
so
its
far,
own state
going
as
to
it travels.
It keeps it counting. That's-
So
that's
here
the-
is what the encoding for line looks like. Sorry, 1 second. So here's what the encoding for line looks like, and this is the simplest machine that we've got. This is the simplest machine that we've got that can actually do what you just asked. So a line cell, this is the definition of a single line cell. So whenever a line anywhere takes a turn, it's going to do this. It has one piece of internal state, which is its position, and the default is 0, although it might be given a position by something else, by its instantiator. If its position is less than 10, then we're going to spawn to the right. We're going to spawn to the left. We're going to spawn at -1, 0. We're going to spawn a copy of ourselves, and we're going to give that newly spawned copy an increment of our position as its position.
So you sort of know your number reference within the system of
Yes.
like where you respond in the computer. You know if you were at 0, 0 in the tiling system.
So you have a piece of state that says, I am number 0 of this line, but you don't know globally where you are. So let me
Basically,
Your coordinate system is entirely local to you.
Yeah. So this line here, this cell here knows that it's cell 0 of the line that I just spawned. And this cell here knows that it's cell 10 of the line that I just spawned. Although there's a little bit of a trick there, because what it knows is it contains a piece of state that says it's 10. You can imagine some kind of virus cell running around and changing the internal state of lines to something random, and then it would know a different thing for sure, which would be wrong, but it would still know it. So the way that this works is This one, when it spawns a new cell, and it's always spawning new cells to its left, it's going to give it one more than its own state. And this one, when it spawns a cell to the right, it's going to give it one less than its own state. But that's all you know, right? So there might be another line down here. In fact, here is another line down here. This one also knows that it's the 0th cell of that line. Right? But these are different zeros. And this one doesn't know, what this one does not know is that I'm at 3616 of the global grid, because it can't possibly know that. When it wakes up, it knows I am 0, 0, and there's a thing to my left, and there's a thing to my right, and there's a few more things surrounding them. And I can address them in a relative fashion from myself, but I don't know what their global address is, and I can't pass that on as a message. So that's sort of, that's the simplest one. We can take a look at some of the writer source code, although I don't know that we will have enough time possibly. How long do we have here, by the way? Like, when do we get kicked out?
8:30, 9.
Okay, cool. So we've got some more time.
No, that's fine. I'm good with.
All right.
I totally get out of the router now.
Awesome.
From within, it's boxing code.
Yeah.
But as for its reset state, I don't think I'm
Yeah.
too curious.
Yeah. The thing that I mentioned you'd be mildly disappointed by is I thought that what you were asking was, well, how does the router know to stop at the edge of this world that we've
Yeah,
got?
that kind
And
of stuff, yeah.
it doesn't. That's hard coded.
I see.
So this particular router is 25 wide, but that 25 is actually a piece of internal state in the router cells. So if we wanted larger routers, what we would do is modify that state, or we would write cells that walk along and say, you, router, make yourself bigger, and then this would expand.
What's the alternative?
The alternative to keeping that encoded as state is keeping it encoded as a constant, and then it can never change. Are there other alternatives? I guess there are other alternatives, which is, well, so remember I said the way that I originally wrote router bleach is it was basically just gray goo, but with a whitelist. And that whitelist included router cells and router shield cells. So what would happen basically is this thing would naturally grow to encompass all of the space that it could possibly find until it hit a situation where the rest of its light window was covered by cells that are in its whitelist, and then it can't sort of advance any further. And that's kind of an implicit way of saying this is how you are limited, right? There was nothing in that program that said you must stay within some enclosed box of space. The problem then is if anything cracked open those sort of implicit limiters on its expansion, it would continue expanding and not stop. And I don't know how important it is to stop that. Maybe we need like a virtual EPA or something to tell us these things.
The idea with that gray goo version is it's better because it's a simpler program.
So let's take a look at that.
What's the difference between the state and the constant?
So the constant can be modified from inside of the system.
Can't or can?
Can. So the constant is a thing that's sort of in the substrate. Like, the tile and the underlying cells know what this constant is, and it's expressed in the language that I'm writing in here. But once I've instantiated a thing, a cell can't change one of those constants. Right? Because the language that I'm allowing for the code inside of a cell to have doesn't have that capability.
So it's part of the runtime somehow?
Yes, it's part of the runtime. Whereas if I encode this as state to a cell, then you can imagine another cell, or maybe even this same cell, having the capability to move in, like, without resetting this part of the system, and just saying, okay, that's tweaked now, you're bigger. Like, you get more playroom.
But it can change the code just as easily as it can the state, right?
So it can change its own code. I've tried to be relatively clever about what you can do from inside the code that is running inside of a cell. There's a few things that you don't want here. So I'm making the assumption, remember, because the way that I'm conceptualizing this is each cell is its own sort of machine. So I'm assuming that each machine is going to at some point have to get a packet of code from somewhere and run it, and that machine is not necessarily going to be able to trust that code. So what I want is for it to be able to validate that code for certain things like, let me eat all of your memory, right? There's some stuff that's malicious at the hardware level that we would like to prevent. So as a result of that, you kind of want a restricted language to be active inside of these cells that still lets you do a lot of expressive things, but not necessarily do things like mutate arbitrary memory inside of your target machine. You want to have sort of a restricted set of state that you can modify that is writable by anybody in your event window, but you don't want it to be able to like peek underneath and look at your CPU instructions, for example, necessarily. Does that answer your question? If you have further questions, I want you to ask them, because I don't want to leave you hanging on this.
I feel like there's a lot of trade-offs in here.
There are a lot of trade-offs in here.
I'm just wondering if it's like a logical extension of object-oriented programming in that it's about message passing largely, and the modification to traditional object-oriented systems would be that the address space is constrained in a way. I can't just talk to any old object in this whole system.
Maybe.
I'm allowed to talk to.
So in an So depending on the object system, you might already have constraints like that, right? If you're doing foreign object calls, for example, across a network boundary, you already have to do something different than if you're calling a local method. And that's the sort of boundary that we're kind of enforcing here. So yeah, you can think of this as an extension of object-oriented programming, although how useful that is depends on what part of object-oriented programming you think is useful, I guess.
Does it hurt anything to do the inter-cell communication in a more civilized fashion? Like using shared nothing message passing instead of unhooking your state directly?
Maybe. I haven't thought about that in particular. So if you did that, so that might be one way of getting around this locking problem, right?
The locking problem?
So the reason that we have this issue here that I mentioned at the beginning, this issue of we need to lock this entire, well actually yeah, this one's probably the better illustration. The reason that we have this problem of you need to lock this entire region even if maybe some bordering cells are off on another tile, is because we want this middle cell to have the ability to write to all of those cells in a destructive fashion for the duration of that write. And if we allow inconsistent writes, that's the place where a lot of bugs are going to start emerging. If we take the perspective of actually we don't need destructive writes, we can do all of this by message passing, like an Erlang or object style message passing system, then maybe we don't need to make those locks happen at all, right? Maybe then each cell has an event queue or something like that, and it's running local state updates without having to expose any of itself to network pokes.
I think you would still need locking, because if the message involved doing yet another write to something, you do need a lock of everything within your light window. Otherwise, things like the bunny, you could end up with one tick later where it had filled up everything because they each observe different things.
Yep. So I'm not sure whether that's a problem with locking or a problem with the bunny logic. So the problem that's being expressed here is if you had the non-locking problem, the way that you basically have to think about it at that point is, I need to be able to act on partial neighborhoods. Right? In other words, I might not get the full 40 unit grid when I start my logic. I might get 5 of those cells to work with, and then a little bit later I'll get another 6 of those cells because they're not coordinating. And at that point, doing something like I want to take a census of my surrounding environment, that gets really weird and maybe not worth it at that point. So the answer there is, you're right, maybe we need locks if we want that style of programming, or the answer might be, maybe that's just not, we don't want that style of resource restriction. We want the other one that's just sort of fully contained and probabilistic, but it doesn't care about what its environment looks like at the time that it runs.
About any of its environment.
Yeah.
It has a window of 0 of itself.
Well, so what I'm talking about specifically is the dereg approach, right? The dynamic regulator does the same sort of population control stuff as the bunny, except it doesn't, okay.
Well, right, the alternative is to make it more like a distributed system where every cell could ask neighbors in its for their state, and then it would get those answers back at some point.
Right, the question is though, if you have any light code at all, you need to have some form of locking or synchronization between them.
To be able to program in the kind of destructive mutated style that we're seeing here.
Even in the message passing one.
So I think we can devise systems that still have a lot of properties that we would like if you have unreliable communication communication or arbitrarily delayed communication of state back to you.
Yeah,
right?
so I agree that you would be able to, but it would just give you a much weaker programming model because you can't rely on being able to do things like take a census of how many people
Yep.
are
Right.
even in my direct vicinity.
But at the
Have-
same time, you can rely on others around you not directly poking your state.
Yeah.
So it's weaker in some ways, but it's stronger in others, I guess.
Yeah.
It's strange that we're talking about robust computing, but each of these cells is so fragile on its own.
Yep.
that it's so easy to compromise.
Let it fail.
Yeah. No, this is the classic story about how do you build reliable systems out of unreliable parts is the question that we've been dealing with basically since the beginning of the computer industry.
Somewhat before that.
Right.
Yeah.
It is interesting
Yeah.
to think of this model in highly destructive environments. Like if we were sending a probe to the sun or something, and we knew that cosmic rays were going to knock out a bunch of things on the way there.
Are they going
Yeah.
to flip bits too? Now?
Yep.
Sorry?
Are they going to flip bits as well?
Yeah.
Cosmic rays.
Yeah.
Yeah,
Yep.
definitely. They're going to do all kinds of damage.
Yep.
But that's okay. It'll rebuild itself.
Well, it'll rebuild itself to the extent that it wants to, which might be
Yeah.
flipping a bit to be a line that is 10,000 meters long instead of 10.
Yeah. Good.
Yep.
So you still kind of
That's-
lose the robustness there.
So this is a further question. This has been clarified in a direct question to Ackley about, hey, your programs are really robust at the macro scale, but actually that source code that you're writing for each cell, that also has the properties of like if a random bit flips in that source code and does what you just said of, hey, instead of doing a 10 long line, we're not going to do a 10 million long line. What do you do about that? And his answer is basically, so I guess I don't think he and I agree on whether we should be looking for a language to express these machines or whether we should be looking for the set of useful machines. So the proposal that he ended up, so a friend of mine ended up emailing him about this specific question. The proposal that he ended up making was, okay, what we really want to do is put forth a dedicated research effort to find out what kind of machines are useful in the space of programming in this style. And then once we have those machines, what we want to do is implement that sort of periodic table of elements on each grid space. And then they sort of have that source code locally in some really, really like hardened piece of hardware, like some write-only memory that never changes and is potentially like backed up in some way so that you can do things like robust storage of this stuff for probes that go to the sun for some reason. What would end up happening then is these things sort of point to the units that are implemented platonically on each board, and you wouldn't be able to create any more new cells. The idea would be that we would discover all of the useful ones and then have those building blocks available. I don't know that I'm satisfied with that answer, because that's sort of... It's not clear to me that such a set exists. It seems like we might keep finding new things that are useful to do based on how far we push this, or we might find this entire thing is useless.
Or new attacks against what you thought was a reliable
Yeah.
machine.
Right, exactly.
It sounds like he's thinking about something on the order of logic gates, though, right? He wants
Yeah.
a primitive set that could be considered a complete set. So we can take and or not gates and build chips out of them. And even if you come up with new gates, which you certainly can, you don't need
There'll be
to
compositions of, right.
computing
Yeah,
hardware,
okay.
right?
No, that's
You
fair.
can always compile down.
Right, but if I find a common set of cosmic rays or bit flips that make your AND gate do something you don't want it to, in the case of a simple AND gate, one bit flip ruins
Yeah.
it.
Yeah. Well, one bit flip on that particular board in the proposal that he put forth. But yeah, you're like there's a non-trivial chance that on a trip to the sun mission, this ends up happening and stuff explodes in ways that we didn't predict.
Well,
I don't
there's
think
a
the mission's gonna work.
guaranteed
No.
chance that a trip to the sun. Well, we've already done that once, yeah, except it was just into Saturn instead of.
I mean,
the sun.
realistically, I think what we ended up running to that is what, fourth or something? Or did they actually do assembly on the machines that ended up doing this? You know more about this than I do, probably.
Which one are you referring to?
So the Saturn probe, how did we end up implementing the software on that thing?
Oh, I did not actually track that. I do know what
Yeah.
it spent its last, like what they did with it and why.
Yeah.
It seems like in general, if you flip random bits in the code of a particular cell, it's going to make that cell malfunction, and it will be overridden by its neighbors.
will it be
That's the
overwritten, or will it
Well, like
turn into
with the code that makes a
gradient?
line, for example.
Yeah.
Yeah.
It gets overwritten
Yeah.
all the time. Each of them is overwriting each other.
But what if a single line cell
Yeah.
has a bit flip where it believes its length should be 10 million?
And it starts
It
writing
will be
its,
the one that overwrites the other.
Sure. So it is possible to have bit flips that cause something like that, and we might want to write code in such a way that no single bit flip, even if it gets through,
I think it's very, very challenging, and I don't know how you do that.
I agree, but
Right? So my length is 1, 1, 1, 1, 1, 1, 1.
A bit flip could still add an extra 1,
Sure.
or turn 1 into a
Definitely
0 in the
add
middle,
extra
and then your length would be shorter than
Yeah, that's fine, because we're robust, so off by 1 is fine. You just don't want off by millions. Right.
Well, I mean, it's like Byzantine generals.
Yeah.
Right? Essentially, like, how do you trust the computer isn't lying to you? Or the computers aren't lying to you?
Yeah.
One question is like, how did you design this? Because it seems like to me, like even something as small as this, you
This-
require knowing the cross product of all the interactions of its pieces in order just to get this right.
Yeah. So, I mean, spoiler alert, I don't have a proof of correctness for this program. So this might be doing something completely wrong that I'm not aware of. The way that I built it was I have a REPL-enabled language that happens to be a Lisp that I just sort of sat down at and incrementally built up. So I started with, okay, let's build up a working cell. Sorry, let's start by building up a working cell Redder membrane. Okay, now that we've got a working Redder membrane, how do we make sure that it can harden itself from outside attacks? And then we had sort of the black border with the yellow stuff on the outside. Okay, now that we've got a delimited cell membrane for this Redder, let's make sure that it can generate, let's make sure that it fills itself with Redder bleach after it's enclosed. Okay, now that we've got Redder bleach, well, let's check that, let's make sure that it can generate messages for itself. And then finally, okay, now that we've got all of the rest of this stuff, let's set up the grid of addressing endpoints so that it can handle these messages and then do something quasi-interesting with them, like write them to standard output, which it's still doing. That's often.
But I think part of the idea is that programmers in general wouldn't be writing these components, right? We'd be writing programs that compile down to general purpose components under the hood that are robust.
Yeah. So
I mean, this is part of his
So.
his table of elements approach, right?
So you're saying that what we really want is like a closure to cellular automata compiler instead of doing doing stuff at this level ourselves? I mean, maybe I don't know.
Well, it's a lot like what we do now.
It is a lot like what
when
we do.
I want a scalable database,
Yeah.
I have an application that needs
Right.
a scalable database. I don't write a scalable database as part
Right.
of my application. I grab one and
Yeah.
Yep.
along with a tiny bit of my extra code, which is
Yeah. No, I agree. This is the problem, is that like when I first heard this expression, it was like, wait, I disagree vehemently, but I'm not sure what my point of contention here is, and then it's sort of the first four that I tried fell apart before I uttered them. And yeah, I'm not sure I can argue with you on that one. It just doesn't feel like the right thing to do. It feels like we ought to be building these things. This looks like way more fun for me, at least. I don't know.
for that. Oh, sorry.
That's sort of a different tack, which is like, this guy's clearly interested in being informed for computing from life.
Yeah.
Have you seen anyone else do something? Inform from not life, but just the universe. A better computing machine that you're slightly interested in, aside from cellular autonomy. Aside from biology, I guess.
Aside from biology, I mean, I guess
Zovic programming? Is that more for chips?
maybe, I guess, sure.
Electrical engineering?
Diagrammatic programming is a thing. That's pretty cool. I wrote a piece on that a little while ago, if anybody's interested.
There's chemical computing.
There
Yes.
is,
Karen Myers does a good talk on that.
yeah. Chemical and I mean quantum computing is a thing right now, which uses like physics level non-locality to perform some computations. I'm not sure how much of this is actual hardware and how much of it is a whole bunch of people talking to committees right now, but if you guys are interested in this sort of thing, Rigetti apparently has a prototype and D-Wave has been a thing for a while.
You can compute with DNA.
Sorry?
It's similar, like if there's a lot of failure in mutations that gets washed away and
Mm-hmm.
just the sheer wide number.
Yeah. Well, this is, so, I mean, if we're on the tack of biomimicry and, like, natural computers, DNA is sort of this really weird thing of, so last I checked, we don't know whether the proper analogy for DNA is, like, the log output of our cells, or whether it, or the logging output of our biological processes, or whether it's, like, the assembly instructions that create us. There's a lot of really complicated shit that goes on inside of actual animals that we don't really know very much about yet. This is sort of closer to that model in that we don't really know much about it yet, but I don't know how analogous they are, I guess. They look pretty, like, it looks like there's analogies between them. Yeah?
You did a cell membrane in basically in software.
Yeah.
And he's talking about doing it in hardware. Do you know why he picked hardware as a way of doing
So
that?
he's not necessarily talking about doing it in hardware. He's talking about implementing, so the simulator that I wrote, Lem, or Twirl, it only the only primitive it has are cells and things inside of cells.
Mhm.
We're done. The proposed movable feast machine has an additional element called cross-cell bonds or something like that. And the idea there is that when you have a thing inside of a cell, it might have a long-range link to another thing in some other cell somewhere else. And that link is another element that the hardware needs to implement. And the implementation that he proposes of cell membranes uses that particular long-range bond instead of just making the entire membrane cells. Now, to be fair, I mentioned that this is a demo that I saw of Ackley's. This is actually a thing that he built as well, so I'm not sure whether the latest model that he's working under is the long-range bond model of cells, or this idea of all membranes are composed of cells purely, because he's done both and I'm not 100% sure which one came first. But so now that I've given this talk and done a bunch of work that prototypes this stuff, I think I'm going to actually have to do something about talking to this person so that we can figure out where our theories have, what our theories have in common here.
The demo 2 years ago used this model.
Right. Okay. So that sounds like it's more recent than the paper?
I think so.
Okay. Okay. It's one of the questions that I'm going to ask him.
Yeah, my sort of reaction, well, particularly with this router, is what you really want in a router is a specialized outer cell that's actually a target of a smart wire.
Mm-hmm.
And the routers would, like basically smart wire in, smart wire out kind of thing to actually route in a system rather than have internal consumption that sort of by definition doesn't go anywhere.
Yeah, well, I mean, it comes from somewhere and goes somewhere, but those other places are outside of the context of the program right now, right? The representation that we've got, so right now these are writing the standard output, but you could easily imagine these each having like the other end of a TCP endpoint and writing out to some other machine on a network. Where that would just sort of be outside of the context of our program. But you're right, if we took the approach of our full program must be represented in cellular automata style, then probably what you would want is something like a wire going from this router to somewhere else, and then picking which wire will be the one transmitting data is going to be the function of the router.
Yeah, I was sort of thinking that the tile machines basically enforce that, don't they? Like you can't connect into the middle of a tile. You have to go from an edge.
It depends on the primitives, right? Like it might be the case that one of the primitive machines that's available to one of these tiles is write this to a network interface. And then anything that any appropriately addressed data that component eats will get transmitted outwards. But you need a way of the system exposing that kind of out of band machinery to you. You can't do that yourself from inside the system.
I don't know that there's been a lot of thought spent on I/O with respect to this.
Yeah. Actually, that was sort of like the first. I figured, as my comment on the Slack channel was this thing swims in the soup of IPv6, right?
Yeah.
The first thing you really need to write is an IPv6 handler.
Okay, yeah. All right.
Great.
Sounds like we're good. Thank you.